Hello everyone. Thank you for joining. Uh, our speaker for today is Mr. Faraz William. So, thank you very much, Faraz, for agreeing to deliver this talk. Um, a little about Faraz. He did his bachelor's degree from Forman Christian College, University Lahore, and after that, he got the opportunity to study his master's at Kamsat University, Lahore campus under the International Mathematics Master Program. And currently, he is a PhD student at University of Udine. And he primarily work with stochastic delay differential equations. And let's hear more from Faraz. So over to you.
Okay. Thank you, Wajid. First of all, you can hear me well, right? Okay. So, hello everyone. Welcome to this short talk of today. Uh, well, I have kept it pretty simple, so you don't need much of previous background to understand all this stuff. And okay, so let's begin. So the topic for today, it looks a bit fancy, that when the past matters, an introduction to delay differential equations. So I will justify this phrase that when the past matters later on. And yeah, so Abhijit have already told you about me. I'm a PhD student at the University of Udine, and I work with stochastic delay differential equations. So I will start with very basic. So let me move to the next page if I'm able to. Okay, so the outline for today is that we start from the classical initial value problem. Like I'm sure all of you have seen at least one course of differential equations. So some initial value problem in the case of differential equations. And then I will define something called as dynamical systems generated by differential equations. In this talk, dynamical systems would not be very important, but it's still important to introduce it because maybe I will use the word dynamics or something like that. And then, of course, the main topic of today, I will introduce the delay differential equations and something about when their solution exists and etc. And of course, I will tell you the difference between what is the difference between a delay differential equation and what's the different and an ordinary differential equation. And then, of course, what the thing I work with, the stochastic differential equations, the stochastic delay differential equations. And since I mentioned about numerical methods in my abstract, so I will talk just one slide about the numerical methods for stochastic delay differential equation. So let's dive into it. Oh dear. Sorry, it's a bit new for me. Okay. So the classical problem, I'm sure all of you have seen some differential equation at some point in your career that it looks something like that, that the derivative, okay, this is, we talk about here, the linear differential equations just up to the first derivative. And the same theory can be extended to the higher order differential equations. So the derivative of a function x of t is given by some function f of x of t, and we interpret t as time starting from some t naught up till the final time t. And then this is important, we are given some initial condition, and initial condition is given just at one point. You're given one value at one point, the beginning of the time for us, right? That's what the initial condition is for an ordinary differential equation. And then I move to the dynamical systems. Let me admit this. Okay, what is a dynamical system in a very general sense? Maybe some of you have studied some course in dynamical systems. So a dynamical system is a triplet. In math, we often define things as triplet or pair of two things, etc. Like in group theory, we define group as a set G along with some operation. So in dynamical system, we define this triplet as the dynamical system, where this calligraphic T is the time set. X is something called as state space. I will tell you what it is on the next slide. And T of T is something called as the evolution operator. So T of T needs to satisfy these properties. So at 0, okay, what does T of T do? When you apply T of T to some point x naught in your state space or some point in xy plane, for example, it moves you forward in time. It tells you where this point will be according to this given differential equation after t units of time. So of course, T of 0 is just the identity, because since no time has passed, you will stay where you are. And it has to satisfy this technical condition that if t of t, the t of t plus s must be equal to t of t composed with the t of s. Let me move carefully to the next page. Sorry.
For us, you mean T is some kind of additive group, right?
Well, yes, I think you're right. I think what, if I understand correctly, you're right. So for every t, right? Ah, you mean the second condition. Wait, sorry, let me go to that. This one, right? Hello?
If you want to add T plus S, you need a group structure on T. I mean the time set.
Okay, let me maybe I will try to explain a bit more and maybe that will clear it up. So T of T is a whole, I should have put it like a set. T of T is a whole set of operators. It is not just one operator. So for every T in the time set, there is a corresponding T operator, capital T operator. And does that answer your question? So it's a whole set and each of them moves you forward or maybe even backward in time.
And your notations are very confusing. So I mean T, the time set. There it
Okay.
needs to have some group structure.
Ah, you mean the calligraphic T? Okay, what about it?
It should have some group structure because you want to add and subtract.
Well, not really, because in the next slide, I will going to show you that it is just, for example, we can also take it as a positive, it's just the set of positive numbers. So I don't think it needs to have some kind of group structure. I think what you're saying is that it should be closed under operation, right? But I don't think
There's
that's necessary.
some addition involved. So I mean, you should be able to add and can you if you are at 1, can you just go back to 0 by just reversing the time? This should be possible.
Okay. I think you're okay. I think I understand the question. You're saying that there should be some kind of structures through which you cannot just take T to be anything. That's what you're saying. Like you cannot just take it, I don't know. Well, but still, I am convinced by the fact that you can take it because there are dynamical systems where you take the time to be even discrete. So that needs not to be a group, right?
Sure, you can in that case you can go back and in time, but sure, if you just consider the forward flow, but still you need the addition structure and the time set t.
Hmm.
Yes.
I think you're right. Yes, because other than that, it could get we could get some points where we cannot even we are not even allowed to take.
Yeah.
Let's move forward because I work mainly with the dynamical systems generated by the differential equation. So I always tend to think from that point of view. I think what you're thinking is from more generalized point of view. Let's move forward. Let me. Okay. So the ordinary differential equations indeed satisfy the properties of being a dynamical system with the time set as usually we take it as positive real numbers, right? The solution x of t is the state of the system at time t, and the evolution operator t as is defined as this way. So if you want to see the state of the system, x of t is equal to t of t applied on the x naught, and where x naught is the initial condition. So you apply the evolution operator on the initial condition, and it gives you the state at time t. Let me, okay. In case of ordinary differential equations, the evolution of the underlying phenomena is described by an ODE that is uniquely determined by what is happening now. So what it is trying to say is that, for example, in the case of ordinary differential equations, the only thing you need to move forward, by move forward, I mean to draw the graph of the solution, for example, is the initial condition x of t equal to x naught. That is the value of the state at time 0. That's all you need, right? However, it is not difficult to argue that more realistic description of the certain behaviors could be attained if we let the evolution depend not only on the present situation, but also on the past history. I think there is an example on the next slide that will explain it more in a better way. Sorry. Delay and okay. The motivating the concept of a delay differential equation. So what I said is that you let the system model depend not just on the present state, but also on what was happening before that. So assume that we are trying to come up with a simple model with delay present in it. So assume that there is a set of juveniles. There are juveniles that become adults after tau units of time, where tau is positive. And they survive the juvenile period with p greater than 0. Assume that the mortality rate for the adults is m greater than 0, and the birth rate is b greater than 0. If we denote the x of t, the number of adults at time t, and r is some kind of constant, the product of the birth rate and the probability of surviving, the evolution of the adults is described by. So this is a differential equation that describes how the number of adults at any time is changing over the time. And of course, the number of adults x of t, which is the solution of this differential equation, depends upon how many juveniles were present tau units of before tau units of time. If there were like 18, 20 juveniles tau units of time before, after tau units of time, there should be either 20 or less than that number of adults present. So the term, this constant tau greater than 0 is called as delay, and this term is called as the x of t minus tau is called as the delay term. This expresses the fact that the newborns become adults after tau units of time. The differential equations involving such terms are called as delay differential equations. So this is an example of a delay differential equation. Okay. To completely describe a problem, we need some initial conditions. For example, in case of ODEs, we need the solution at the initial time t is equal to 0 or t is equal to t naught, whatever you select as your initial time. But in case of delay differential equations, the situation is a bit different. The problem is that you need much more than just the initial point. You need more information than that. And I will try to justify it. Okay. I think this is supposed to be the next slide. Okay. In the delay problem described above, which you saw just now, there is a term, this one, x of t minus tau. The initial conditions are more demanding, right? Consider the following picture. So, for example, if you have this picture and you can imagine tau is 4, right? So each time you try to deal with this term, for example, if you put t is equal to 0, you are moved back in time by 4 units of time if tau is 4. So if you want to know the value of x of t minus tau if you not want to know the value of solution at t is equal to 0, you need this term, which is equal to x of minus 4. So you will need the value of the solution, which is somewhere here, at minus 4. But it's the same for all when you move forward. For example, at 2, you will need the value at x of minus 2, because this term keeps making you go back by 4 units of time, right? So up till the first delay, that is up till the time t is equal to 4, you will always need to go back in the history to get all these values to describe the problem completely, right? So you will need a whole curve here, right? From minus 4 to 0, a whole curve here, which will be our initial conditions. So now the initial condition is not just a point, it's a whole function from minus tau up to 0, right? Maybe there is another picture somewhere. Okay. Sorry, I'm just not very familiar with it. Is there anything else? Oh, okay, no, this is the one. Therefore, the correct way to define an initial value problem with delay is the following. Yes.
You may want to go a little slow, maybe, so that
Okay.
you are a bit fast for me.
Okay. Yeah. Also, if you have any questions, just stop me. Okay. Right. So in the above diagram, it is clear that for an equation involving delay term of the form x of t minus tau, for example, tau is equal to 4, to describe the problem completely, we need all values of the solution from -4 up to 0. So we need a whole function from -4 up to 0, like I showed you in the picture. Therefore, we call it the history function. We require the knowledge of history of the solution at x of t, at least in the past interval minus tau up to 0, right? So we need a whole curve to describe the initial conditions. Okay. So this is what a usual delay problem would look like. You take the derivative, there's a differential equation, x prime of t with some terms and at least one term with delay that moves you backward in time. Each time you try to go somewhere, it takes you back in time by tau units of time. So therefore, to deal with this term, you will always need something called as the history function, which is described by this. And these are the correct initial conditions for a delay differential equation. So this gives you a whole curve from minus tau up to 0. Sorry.
Can I ask you something?
Mm-hmm.
Can
Yeah.
you go back to this system you have written, the problem?
The
The statement of
this
here.
one?
Yes, here.
Yeah.
So for x equal to 0,
Mm-hmm.
you need the value of x at minus tau.
Exactly.
But why not also at 0? I mean, like the present and the past.
Okay, yes, that's exactly what I'm saying. Actually, okay, this works. There's a picture here. I will show you. Okay, let's see here. Let me move this thing somewhere else. So at 0, here the delay is 1 units of time. Tau is 1. So if you need to see the derivative, the differential equation, x prime of t, put t is equal to 0 in that term, right? So of course you need value at x is equal to 0, x of 0. I think that's what you were saying. Yes, of course you need it. But I'm talking here, I was talking about what do you need to do to deal with that particular term. Where does that particular term takes you? And with respect to what you are saying, when I say that each time you have to go back and you will need the previous term, we will also cover while doing that, like when you go from 0 to -1, you will slowly cover all these values and also cover the x of 0. So you will also cover all the current time values as well.
Oh, right. Okay, I got it. So it's just equation where only the past matter.
Yes. If I hope that clears it up. Okay. Okay, so this was the equation. Okay, but there is something more to it. Here I have, there is one particular fact that I'm going to describe, but I have not written much about it in the slide because I didn't want to make it complicated. So now this is like the formal definition of a delay differential equation. So given a tau greater than 0 and the state space which I described, which for the differential equations were just the set of points x of t1, x of t2, x of t3. But now this state space is a space of functions, the space of continuous functions from minus tau to 0. And and then this right hand side of the problem is given by f is a function from some function of xt, which is the state. I will tell you why the xt is now in the subscript. Okay, do not get confused by this word. A retarded functional differential equation is a relation of the form. So retarded functional differential equation is like, let's just say a generalization of a more general form of different delay differential equations. It's a generalization of delay differential equations. But for now, you can just think of it as a delay differential equation is a relation of the form x prime of t is equal to f of xt. Xt is now a function. What is and how is it described? Xt of theta is defined as x of t plus theta, where theta belongs to minus tau up to 0. So earlier in the case of ordinary differential equations, we start with a point and we, by some method, do not think about how we get the solution. Suppose you have a solution. All you need is just the beginning point and you start drawing the graph of the solution. But here we need, now we have concluded that we need a whole history function from minus tau up to 0. So I think I can describe it better from the picture if I'm able to go there. Here somewhere. Okay. I will move this somewhere. So if the delay is -1, right? Delay is just 1. So you need this whole history function, right? And instead of studying it point by point, like we study it in the sense of ordinary differential equations, now we are studying it interval by interval. So we study it from minus tau to -1. We take it, this is our state, right? From -1 to 0. Again, this is another state at time. So the state at time 0 would be this whole curve from -1 up to 0. And the state at time 1 would be this whole curve from 0 up to 1, right? And that's what that equation is saying. Let me go back here. I'm sorry. Okay, we have seen this. Okay, somewhere here. Okay, let me just.
Faraz, what is it like? What is popping up on your screen that disturbing you? Is
Oh,
it
no,
like the?
no, it's
Go ahead.
just the problem is with the scrolling. Sometimes it lets me scroll, sometimes it doesn't. I don't know what's the problem.
But maybe like when you scroll, you just say like use the arrow button when you are in the read mode.
Sorry, how?
So when you are in the read mode, you just use the arrow button
The
on your keyboard.
yes, that's what I'm saying. I was trying, but earlier it was working, but at some point it stopped working.
Ah, okay, that's okay.
Okay, so here we were. I will go back into the read mode in a bit. So, okay. So this is what I was trying to say from the picture, that each time now we are studying it interval by interval, and state now is a function. And but now all those functions were in different domains, from -1 to 0, from -2 to -1, from 0 to 1, right? But we want them into one single domain because we want the state space to be this one, the space of continuous functions from minus tau up to 0. So each time we fix the time t, and xt of theta is defined as x of t plus theta. Now t is fixed and theta is the thing that is moving you through the interval, right? So now each state at every point is a whole curve, right? In the domain minus tau up to 0. We call tau the delay interval. We call tau the delay, the interval. This has the delay interval, and xt, the state at time t, which is now a function. Okay, so when does the solution for a delay differential equation exists? So this is a theorem that if f is locally Lipschitz, what is f? The right-hand side of the delay differential equation. Then for any phi in the state space, in the space of maybe even bigger than the state space, in the space of continuous function, there exists t, which is the evolution operator, and a unique solution phi of the delay differential equation in the interval minus tau up to t. The solution is locally Lipschitz with respect to phi. So the only condition we need for the solution to exist, that the right-hand side must be locally Lipschitz, at least locally Lipschitz. Maybe even sometimes we need globally Lipschitz for other purposes, but for solution to exist, we need it to be a locally Lipschitz.
Is
So
it the same Picard argument iteration or fixed point argument?
for the proof of this, you mean?
Yeah.
I think it's the same argument as for the ordinary differential equations,
Yeah.
but I do not really remember the proof steps by step.
Okay, I get it. I know how to do.
But what I remember is that it's definitely the same idea of the proof.
Right. I mean, you just take initial condition by this initial function, history function.
Yeah. and you consider the state as the function from minus dot to 0. Okay. In case of ordinary differential equations, okay, so here I'm trying to describe what time is it? Okay, I will try to be fast. What is the time constraint up till what time we go?
I think you are right on time, so you don't need to be fast.
Okay, okay.
Yeah.
Okay, so in case of ordinary differential equations, if f is globally Lipschitz, so now I'm trying to tell you at least one difference between ordinary differential equations and the delay differential equations. So in case of ordinary differential equations, if the function f, which is the right hand side of the problem, the differential equation, if f is globally Lipschitz, then it is enough to, so f being globally in Lipschitz is enough to extend the solution backwards in time. However, in case of delay differential equations, this is no longer the case as illustrated in the upcoming example. So if f is globally Lipschitz for ordinary differential equations, you can go even you can even get what was happening before the initial conditions. But let's see what happens for the delay. So
Can you
consider this delay differential equation, which is very simple, like a tie problem. So x prime of t is just x of t minus 1 for tau greater than 0, for t greater than 0, and some history function defined on minus 1 comma 0. Okay, in this case, the right-hand side is globally Lipschitz for sure. So for sure, in the interval minus 1 to infinity, the solution exists because because it's globally Lipschitz. So for the interval minus 1 comma 0, the solution must be the history function itself. And it should satisfy this one. So we use this one, right? It is just a weird trick that we use, that the phi of t, which is the history function, is same as the solution. And it must be, so it's like putting t is equal to t plus 1 in this one, right? So you put t is equal to t plus 1, and this the right hand side becomes x of t, and you get the solution. But now the problem is that you want to extend it backwards before minus 1. From the first two equalities evaluated at t plus 1, we have, so this equality you evaluated at t plus 1. So x prime of x of t plus 1, sorry, this is just a trick. So x prime of t plus 1 is that the phi prime, okay. I will not go into the details because I don't want to think about it, but you can get this equality from the previous one very easily, right? But the problem, when you look at this, the problem is that from the problem we have x prime of t is equal to x of t minus 1, which implies that x prime of t plus 1 is just the x of t. Problem is that when you look at all this stuff, there is a prime on the phi, right? So whenever you try to go backwards, go back in time before before the interval minus 1 comma 0, you will have to put, according to the problem, a prime on the phi, like you will have to take the derivative of the phi. But the problem is that you could not just take the derivative of phi, because the state space, as described previously somewhere here, is the space of continuous functions from minus tau comma 0. So it is just continuous. We do not know that if it is differentiable or not. It may be in some particular cases, but to go back in time, we do not just need the global Lipschitz like in the case of ordinary differential equations. We need it to be more than that. We need the history function to be differentiable, at least differentiable, right? So this is one difference between ordinary differential equations and delay differential equations, that if you want to extend your solution backward in time, you will need the history function, not just continuous, but also differentiable. So this is again a picture trying to describe.
But that is also the case for the classical initial value problem. It's this, the initial condition is constant, so say anything you want. So just by any regularity you expect.
I don't understand what.
When you said there's the difference between the classical initial value problem and the delay, because in the delay you want the history function to be differentiable.
Yes.
But
So
this is the case for the classical problem as well.
for the classical problem, usually as much as I know, the global Lipschitz, the F, the right-hand side, for that to be to extend the solution backwards, the F being global Lipschitz is enough. So,
Right.
right? So that's
Okay.
what I was
I
telling.
don't. Okay, but what about the delay?
For the delay, you need the history function. Let me try to go back. You need the history function to be differentiable. So even though you have the global Lipschitz condition, as you look at the problem, you still need the history function to be differentiable.
But in the classical case, the history function is this initial value constant.
Okay.
And it is
And
differential.
maybe,
I'm not
and
sure
that's,
how it differentiate this from classical.
okay, I think what you're saying is that the constant function, whatever that is, the initial condition is of course differentiable,
Yeah.
right? In case of ordinary differential equations, since the constant function is differentiable, so this condition of being the history being differentiable is automatically satisfied. Is that what you are saying?
Yes, so that's true. That's what you are saying. But it's not something that makes delay differential equation different from classical. I mean, it's not a common feature that differs for both. So it's not a difference. It's just an extra requirements that you need for.
Okay, I think you have the problem with the word difference, right? So, okay, let me try to rephrase. What I'm trying to say is that to extend the solution backwards in time for the delay differential equations, you need one extra condition. So it's not difference in the sense that you would usually think, but it is something that you need.
Okay, thank you. Now I got
Okay.
you.
Okay. Okay, this is a picture that I have shown you multiple times. I was what these cross represent is that if you want to extend the solution here in the backwards in time, you need this history function, which is this one, to be differentiable, even though here it looks differentiable, but in general, it needs not to be differentiable, right? Okay, up till now, everything was just fundamental. You didn't need much of previous knowledge, right? So now I'm trying to tell you something about what I do. And for that, well, primarily I do a lot of numerical analysis, but I haven't included that in this presentation. But here I will tell you at least something about what is a stochastic delay differential equation. So for that, I first need to tell you what is a Brownian motion. So maybe some of you have taken some course in stochastic analysis or something like that, or in advanced course in probability theory. So you might know something about Brownian motion. So first of all, Brownian motion is not a deterministic process. Deterministic means something that you can just predict if you are given some information. For example, if you roll a die, you do not know what is the value that is going to come up on the die, right? So that is some kind of process that we call as a random process. So Brownian motion is also something like that, a random process. So W of t is called a Brownian motion and is a random process satisfying the properties. So a process is called as a Brownian motion if it satisfies the following properties: that W of 0 at time 0, it is always 0. So W of T1 minus W of T2. So the difference between two Brownian values, we call it the Brownian increments. They are normally distributed. So normal distribution is like a distribution function for some, in the probability theory, you might have seen it. If you do not know it, don't worry. Let's just say it is some distribution function, right? With the mean 0, the expected value is 0, and the difference between the time is your variance. And the Brownian increments, W of Ti minus W of Tj, they are independent of each other, right? And yeah, so these three properties needs to be satisfied for some stochastic process. When I say stochastic process, that it means that at every point in time, it takes some random value, right? So these are the properties of Brownian motion. So why am I telling you suddenly about Brownian motion? I will show you on the next slide. Because I wanted to introduce something called as stochastic differential equations. So here, this variable x of t is not a deterministic variable. It's a random variable now, right? dx of t is equal to f of x of t dt plus this term, which is the stochastic term here, some function of x times dw of t, where w of t is the Brownian motion. And but you should remember that this equation, even though it is called as a stochastic differential equation, is not really a differential equation, because this term here, w of t, is not differentiable. If you look at its graph, I wish I had included some graph of it. If you look at its graph, it is very rough. It is so rough that every point is pointy on it. So you cannot really draw tangents on it. So it is not differentiable. So this is just a shorthand notation for this integral equation right here. So for just thinking process, you can just take integrals on both sides. So it would be x of t minus x of 0. You can think that the initial time is just 0, and the integral of this term and the integral of this term. But you see, okay, you understand this term. This is just an integral. If you can calculate it analytically, very good. Otherwise, you can use some numerical method. But what is this? The integration with respect to the Brownian motion. This is something new. In the integral equation, the integral, this one integral, the integral with respect to the Brownian motion, is the so-called Ito integral. So there's a whole something called as Ito calculus to deal with such kind of terms. The integral is not deterministic, and in most cases, it is not possible to calculate it analytically. Therefore, it must be calculated numerically. So how to calculate it numerically? That's not the point of today's talk, but let's just say there are ways to calculate it. The general form, okay. So usually that's why we call it stochastic differential equation, because usually we use this form to write it and we don't use this integral form. But we always try to keep at the back of our head that this term here does not really exist, like the dw of t doesn't really exist. So, but in general, with delay, so just like you can introduce delay in the ordinary differential equations, you can also introduce the delay term in the stochastic differential equations, just like the examples of juveniles and everything. So, or for example, in the stock market, you model some phenomena happening in the stock market by a stochastic differential equation. Okay, why would the phenomena in the stock market be modeled by a stochastic differential equation, or why do we even need stochastic differential equation? Because the problem is that, I will show you here, that, okay, there are phenomena, for example, in the stock market that can be modeled, about which you can get some information. You can get, okay, that yesterday the price was that, or some other information, but there is always some kind of noise. There is always some kind of things that you can just never predict, right? Some kind of randomness involved. So to account for that, we introduce this Brownian motion term into our well, yes, you could even say ordinary differential equation, because if you remove this term, the whole thing becomes just a deterministic process, right? To account for that noise, the things that you cannot predict, you add this term into your equation, and now you have added the noise, the things that you cannot predict. So I was talking about the example of the stock market. So of course, the price of a stock today might depend what was the price 10 days ago or a month ago. So you can introduce delay in the case of stochastic differential equations as well, right? So I'm mostly done by up till this part, but I will now just show you some examples that I found on internet in some really good papers about the models that describe the stochastic delay differential equations. So something called as logistic equation. So this is like a population model, which represents the evolution of the population x of t with the intrinsic growth rate alpha is equal to 2. This is some kind of constant relevant to this process. With time delay, tau is equal to 1. And the noise intensity. So we often call this term as the noise. So that's why this constant is called as the noise intensity. Sigma is equal to 0.4 with the underlying scalar Brownian motion. So this model describes the population evolving over the time, but also dependent upon what was the population tau units of time before. And then, of course, you can have system of stochastic delay differential equations. So this is a predator-prey model describing where x1 and x2 denote the predator and the prey populations respectively with the some parameters alpha, beta, delta. And W1 and W2 are two independent scalar Brownian motions. So what is the point of all this? Is that in all the phenomena that we model, the real life phenomena, we convert it into a differential equation. There are always things that you can never predict. If you are predicting modeling the economy of a country, you have to take into account that some kind of, I don't know, God forbid, some kind of terrorist activity can happen in the country, and that would the investor would just take out their money from the country, right? So to account for such things that you cannot predict, you add this noise into the equation, and that describes the things that you cannot predict. So this is the last slide.
Can
So
you go?
something
Can you go a little bit back?
here.
So the first equation, there is. Can you do some interpretation of what is the first equation? So there is
I can try.
there is x2 but only delayed. So that's what I'm wondering about. So why not at time t as well?
Where
In the
in the
first
second?
equation,
Okay, first or second?
the first one.
Okay.
So you have x2 but delayed.
Okay.
And I mean in the
Okay, I can try. I do not. I have not really worked with this model. I got it from a research paper of a friend of mine. But usually, what it means, what I have read up till now, is that uh, the population, what are x2? X2 are the prey, right? So the number of preys that are the number of, for example, I don't know, the chickens.
Paras, so here x1 is the prey and x2 is the predator. So if you, for example, ignore x2 at all, so
Hmm,
x1 is following the logistic growth here.
okay.
And yeah, and you know, like in the absence of x1, so there is always like a x2 will, um, it will decay with the rate of minus delta. So x2 is feeding on x1 here.
Right.
So x1 is prey and x2 is the predator.
yes, and there is like this minus gamma factor, so it like decreases x1, but only at the delayed times. He said t minus tau. Why not also x2 at the point t?
I think each time you always have to consider what was happening before, right? I think that's yeah, but I think I understand your question. You are saying that why just only the delayed term? Why not the current one, right? That's what your question is?
Yes, because normally it would depend on the current population of the prey as well.
Okay, okay. I wouldn't say I know much about it, but I would say that usually what it means is that the delayed term is the well, you have to just take into account what was there before and you deal with it. Sorry, I'm not able to describe much about it.
No problem, no problem.
Yeah, let's move forward. Okay, since I mentioned something about the numerical methods, so I have just made one slide about it. I wanted to make more, but that would just make the presentation too long. So there is something called as to deal with the stochastic differential equations and the stochastic delay differential equations. There is something called as Euler-Maruyama method for SDEs or SDDEs, right? So what usually, I'm sure you have seen some numerical method, even it is if it is for integration or whatever. So what numerical methods usually do is that they do iterations, and each iteration takes you closer and closer to the correct answer. That is usually what you might have seen in the case of numerical integration or quadrature or something like that. And in case of, for example, differential equations, any kind of differential equations, what you do is that you discretize your domains, the x values, which in our case are the time values, you discretize it, and then you calculate the solution at those discrete points, right? And then you just join them together to create a graph, right? So solution would become more refined if the step from time t1 to t2 is small, right? Which we call as h here. So that is the principle here. The Euler-Maruyama method is one of the classical numerical methods for the solution of stochastic differential equations. The following is the version of the Euler-Maruyama method, and this version holds also for the delay. That's why I have included the delay term. But you can also include it, use it for the ones that are without delay. Just put tau is equal to 0 and it would start working. So you are given with some history function, and the step that you do each time, you discretize your domain. Xn plus 1 describes the value of the solution at time tn plus 1, because you discretize your time as uh, t0, t1 up to so on tn, and you take the previous value times h, which is the step that is like t1 minus t0 or t2 minus t1, right? Times the f value of the stochastic differential equations, like here, this one, the one that is with dt, plus g times the difference in the Brownian, the something called as the Brownian increment, which is like the Brownian motion at time n plus 1 minus Brownian motion at time n. So you keep doing it, and each time you get a solution at each of these times, t0, t1, t2, up to so on. And that's how you plot the points in your solution, and eventually you join them to get your solution. Something about, something general about this is that what I do is that we come up with more numerical methods to solve this kind of problems, right? So for example, as I told you earlier, that in case of delay equations, the state at each time is a curve, is a whole function, right? So currently I'm working on numerical methods that calculates the solution in such a way that you are able to get the curve each time, because this one calculates the solution point by point, right? So instead of points, you get a curve, right? And there is actually, for example, for the stochastic delay differential equations, you would find very less research papers. There are not many research papers in that field. Uh, and the ones that are, for example, even for this example, in that case, the term tau must be a multiple of this h. H is the time step. But problem is that it needs not to be, because if you do that, that just restricts you to a lot of things, right? So what we are trying to do is that coming up with a numerical method in which this constraint, that the delay it must be a multiple of the time step, we are trying to get over this constraint. We are trying to come up with a numerical method for which we don't need that, right? I think that would be the end of it. So thank you so much. If you have any questions, you are welcome to ask.
Um, Thank you very much, Paras, for that nice introduction to delay differential equations and stochastic delay differential equations. Um, Maybe I will just hit the stop button and then we can continue with discussion in Q&A session.